Welcome to lecture series 8051 microcontroller. We continue with the instructions part 3. In today's session we will discuss about the signed additions along with the logical operations with the branching instructions. Okay. So, first we will do the signed addition. Signed addition means mostly it will be suitable only with the 7 bit, because the 8 bit which is a most significant bit used to represent the binary numbers, that is used to represent the sign. If it is 1 means it represents the negative number, if it is 0 means it is a positive number. So, mostly we are using the 2's complement, because after taking the complement only we are performing the representation. Suppose you want to do the addition of minus 2 and minus 7. Okay. So, what we are doing minus 2 minus 7. Okay. So, what is the binary of 2 means 0 1. So, the binary equivalent for 2 is 1 0, for 7 is 111. Okay. So, you will equivalent to 8 bits. Now, we have to take it as a complement because of the negative number. So, 2's complement, if you are taking, what it comes 0 1, after that all zeros become 1 1, right. So, now you read this as a FEH. In case of 7, first 3 is a 1, remaining up to 7 bits are 0. So, if you are taking it as a 2's complement, for that what you get 1 0 0, then remaining all are 1 1. So, by reading in the hexadecimal you will get F9H. Okay. So, suppose if you are started to write the program means you will take it as move A comma FE, then move R1 comma F9, then you can use it as add A comma R1. So, after performing this addition, what we are expecting, it should be a minus 9. So, here you can do the addition, because after taking the complement it will be perform the addition. So, 0 plus 1 is 1, 1 plus 0 1, 1 plus 0 1, 1 plus 1 0, then carry over 1, then 111 become 1, then again 1 1 1, right, 1 again 1 1 1 is carries occur. Okay. Now, we have to check it the MSB. After the addition we have to check the MSB. MSB is a 1 which represents this is a negative number. Okay. So, you put the negative, after that you have to take the complement of that, the 2's complement of that. So, by taking the 2's complement, what you get, first one is 1, remaining 0 0, then 1, remaining are 0, then this is a negative. Okay. So, what you get 1 0 0 1 is 9. So, minus 9 you are getting. Okay. So, now the accumulated value was minus 9. So, this is the way we are adding, right. Suppose you want to perform the same addition, minus 2 plus 7, minus 2 plus 7. So, what is the resultant value? Yes, plus 5. The same operation will be do it. In case of plus number, no need to take the complement. So, now we are taking the another example to add the number minus 2 plus 7. Okay. So, for minus 2, whatever, whenever you are taking the negative number you have to take the complement. For positive number no need to take the complement. So, 7 its binary equivalent is 3 1. So, you have to write it as 3 1, then followed with all zeros, because we have to equate the length. Okay. So, 8 bit positions we have a 8. So, after initializing here the number is loaded with 07H. Okay. Plus 7 minus 2. So, minus 2 is replaced with FE, 7 is considered as it is. Now, by using this instruction addition is performed. So, by adding this 0 plus 1 is 1. Okay. Then 1 plus 1 is 0, remaining 1. So, here it become 3 1. So, it become 1, then 1 plus 1 0 0, remaining all are 0, then 1 is occur, it will be discarded during the 2's complement of addition, right. Now, you check the MSB. If the MSB is 0, what it represents is a positive number, you can write the answer as it is. So, now plus 5 you can do it. Okay. If the resultant value, that is MSB bit position is 1 means you have to take the negative after complement. In case of 0, you just give the plus symbol with the its equivalent binary representation. Okay. So, this is a signed addition how we are performing in the 8051. In the 8051, in case of negative number, sometimes in if you are typing means you can give it as a comma minus 2. Okay. In case of conventional of opcode, then you have to give it in the a comma fe only. You convert into complement, then you feed the input value, you will get the exact answer. So, I think you get the idea how to perform the signed bit addition. The same thing you can repeat for both are negative number or any one is negative or both are positive. If both are negative or whenever you are using the negative number, you have to take the complement. The positive number you simply use as it is. Then after getting the resultant, you have to check the MSB bit position. If the MSB bit position is 0 means the given resultant value or whatever you get, that is a positive value, right. If it is 1 means it is a negative. So, you have to take the complement, then give the negative value. Okay. So, the next we will discuss about the logical instructions. Logical instructions, the basic gates which are AND or NOT will be performed along with the exclusive OR. Okay. The AND and OR are the two operands. These all are the bitwise operators. Bitwise operators, what it states, each bit will be represented logically AND with suppose if we are giving the value A and B means the A is logically AND with B, then the resultant stored in the accumulator. The same thing will be discussed here. Okay. So, the accumulator value will be logically performed with either the immediate data or with the address or with any one of the register, or you can with the indirect registers. Okay. So, these are the way we are using. Now, I will give a simple example, you will get an understanding. So, for that these are the mnemonics we are using ANL, A comma either you can give the immediate data or address, okay, or any one of the registers you can use it, or at register. Okay. So, by this I want to perform the logical AND operation with 73 and 29. Okay. In case of logical AND means how I will start to write move A comma one of the data should be loaded in accumulator. So, 73H, then I will give move R1 comma 29H. Okay. Then you can use it ANL A comma R1, this register format. So, by using this both are logically and the result is stored in the accumulator. Now, I want to know what is the value in the accumulator. So, how it was performed means the given number 73, it is a hexadecimal number, right. So, you can write it in the 4 equivalents. So, 73 means the binary representation for 7 is 0 1 1 1, okay. 3 is 0 0 1 1. The another number is 2 0 0 1 0, for 9 1 0 0 1. Okay. So, now we have to do the logical AND operations. As per the truth table, logical AND gate means if any one of the input is low, the output is low. If all inputs are high, then only you will get the output as high. Okay. So, as per that here both signals are 1. So, I will get it as 1, here 1 0 0, 0 0 is 0, 0 1 is 0, then here 0, both are 1, I will get it as 1, then 0 0. Now, read the number which is 2 1. So, now the accumulated value is 21 after performing the logical AND operations. Okay. The same mnemonics we are using for the OR. In case of OR, suppose I am doing the OR operation for the same input. What is the truth table for OR gate? The OR gate states if any one of the input is high, then you will get the output is high, right. In case of AND gate, if all inputs are high, then only you will get the output is high. Okay. Now, I will do the OR operations, just I replace this ANL with ORL. ORL means what? The 73 logically are with the 29, these all are the bitwise operators. So, bitwise only the operations will be performed. So, here both inputs are 1. So, you will get the output as 1. Okay. Any one of either one or more number of inputs are 1, we are getting the output as 1. So, here one of the input is 1, you get it as 1, then 0 1, here 1 1 1 0. Now, what is the value of this? first one is 7, another one is 1011. So, which is B, right, in hexadecimal. So, after performing the OR operation, you will get it as a 7B. The same thing you can use it for the exclusive OR also. Exclusive OR means what it states, if both inputs are same, then the output is yes 0. Different inputs if you are giving, then you will get the input as 1. So, for that you can use XORL, XORL A comma R1. So, now it will do the exclusive OR operation. If both are same, then you get the output as 0. Here the input is 1 0. So, different input you will get it as 1, same input 0, different input, same input, different input, same input. So, now read what is the value, this is a 5, this is A. Okay. So, after excluding the same number, you will get the answer as 5A. So, the same instruction, just you have to initialize the given number, then you can do any one of the operation. In case of AND, you can use the ANL. One of the data should be in accumulator, another one is either the data or in the register you can do it. Okay. So, these three are more or less same, but here you have to check the resultant by manually do the bitwise operations and expect the answer as either 5A or 7B or 21. Okay. So, these are the two operands. In case of NOT gate, we have only a single input, right. If you are giving A, you will get it as a dash. So, that is why here they were give it as a complement of A. So, the one of the data should be loaded in accumulator. Suppose I have the value of 75, means the 75 is loaded in accumulator, the value is 0 1 1 1, then 0 1 0 1. By giving the CPL, what it will do, this is a value. Now, the A dash will be loaded in the accumulator. What is A dash means? It is take simply a ones complement of that, all ones and zeros are replaced with that. So, here 1 is replaced with 0, 0 is replaced with 1, then 0 0 0 1. So, the new value was 8A. 8A is the complement of 75. Okay. So, this is a way we are using the CPL for NOT gate implementation. CLR-A means it is used to clear accumulator, means the accumulator will be initialized with 0 0. Okay. So, we are clearing the accumulator, so it will be initialized. These are byte-wise operation. Byte-wise operation means we are getting the 8 bits, then we are performing the logical operations. Suppose you want to perform particular bit, only one bit I want to mask it, that case you can use the bitwise operations. In the bitwise operations, what it will do, ANL see with, that is carry with bit, what kind of bit you are giving, that bit positions will be performed. Suppose you are using ANL C comma P 1.5, right. These are the bitwise operator, means what are the special function registers having this kind of facility, that only you can use it, right. Or you can use ANL C comma accumulator 0.5. So, what it represents, the fifth bit position of accumulator is logically AND with the carry. The same thing for OR gate, this is a complement of carry, that is CPL, right. Complement of the carry, if carry flag is 1 means after taking this instruction it becomes 0. The same thing complement of the bit position is set or not, this is clear the carry, whatever it will be replaced with 0, this is a clear bit. These two are the set bits, which is the special function registers, all are right bitwise operators, right. For that, suppose you want to activate the T mode register of 8th bit, that is 7th bit, means you can give it as set bit position of T mode 0.7. So, what it will do, among this format, the 7th bit will be set it as 1. Okay. The same thing in the program status word also, you can give it as set bit of program status word dot 5 or 4, whatever the bit positions you can set it. Okay. So, this is a set 1, the same thing will be cleared by using the CLR instructions. If you want to access the particular bit to perform any kind of operation, means you can use the move C comma bit positions. And one more instruction in this logical operation is rotate and shift. In the rotate and shift, what we are doing, we initialized the number that will be shifted left direction or in the right direction. Okay. So, simply the data should be loaded in accumulator. That accumulated data is shift lefted means what, the D naught value is shifted to D 1, then D 1 is shifted to D 2, and the last 7th bit is moved to the D naught. Okay. This is a rotate left. In case of rotate right, what it will do, D 7 will move to D 6, D 6 will be moved to D 5, like that. The LSB bit position is come back to the MSB position. This is a rotate right. So, we can load what data want to move either left direction or right direction into the accumulator, that content only shift lefted or shift righted. Okay. So, one more thing is rotate via the carry. This is a carry flag, right. So, for that RLC, RRC we have. In RRC means the same rotation in the right direction, the LSB is moved to carry, the carry flag only moved to the MSB. The carry bit position only comes to the MSB bit position. Okay. So, who will inserting the new data, that will be different for rotate right and rotate right through the carry. Rotate right means the LSB data will be inserted into the MSB. Rotate right through the carry means the carry bit position will be inserted into the MSB. Okay. The same thing repeated for the RLC. The another one is swap. Swap instruction, what it represents, only the accumulated content of lower nipple will be interchanged with the higher nipples. Okay. Suppose the accumulated value you have as a 78 means after using the swap A, the data will be 87. Okay. So, for this kind of particular applications you can use the swap instruction. The next instruction is branching instruction. The branching instruction means from the regular sequence of execution will be different or switch over based on the instructions. Okay. Suppose how it will take the switch over means either conditional jump or unconditional jump. In case of unconditional jump means without checking anything, after reading that instruction it immediately go to the specified location, like go to instruction. Okay. What we have studied in early days. Here we are using the unconditional instruction as simply jump instructions, okay, then call instructions, then return instruction. The jump instruction means without checking anything, it simply switch over, right. So, here this having the 3 kind of jumps, which have the short jump and long jump and absolute jump also, JMP, right, then LJMP and SJMP. So, here the jumping address is 11 address, here the jumping address 16, here the jumping address is 8. So, based on the addresses it will be varied. Like that, here also we are using the absolute call, long call and short call. So, what it represents, here we are using only 8 bit address, here 11 bit, 16 bit address, here 11 bit addresses. So, based on the jumping addresses it will be different. Okay. So, most frequently we are using this kind of long jump and long call. In a short jump we are using with respect to the 8 bit. The 8 bit addresses are relative addresses. Okay. Then return is one of the important instruction which is used to terminate the subprograms. These two are the related to subprograms, right. So, the subprograms here you have a sequence of main programs. After executing the call, it goes to the subprograms. Okay. This is a subprogram, this is a main program. Then it simply switch over. Then after that, from this subprogram, by reading the return instruction only, it will be come back to the main program and will continue. Okay. So, for that the return is used to terminate the subprogram, call instruction is used to call the subprogram. Okay. So, during the executions the addresses will be maintained by the program counter. Okay. The sequence of the execution is maintained by the program counter. During the call instruction, what it will do, the corresponding address where to switch over, that will be loaded in the program counter. Before that, the program counter will be loaded into the stack pointer. So, we have pushed the data into the stack pointer, we have write the data, right. So, after reading the return instruction, now with the help of pop instruction we are reading the okay. So, pop the data from the stack pointer and it will return to the main program. Popped data will be loaded into the program counter. Okay. So, the program counter initially run with the main program, now it was started with the subprogram. After terminating or after terminating the subprogram, okay, the stored value from the stack pointer is loaded into the program counter. Now, the program counter will continue its regular execution. So, these are the branching instructions which are unconditional. In case of conditional means the condition is takeover with respect to the program status word. In the program status word we have a 5 bits, right, carry flag, right, parity flag, then 0 flag, sign flag, overflow flag. So, based on this it will take the condition. How it will take means jump carry. Jump carry means if carry flag is set, okay, with the relative address we are giving. So, jump if carry flag is set. Jump on no carry means the same address we are giving if carry flag is not set. Either you can say it is not set or C equal to 0. Okay. This is a set value, this is a reset value. Same thing you can do it with respect to the 0 flag, jump on 0, jump on no 0. Okay, for this we are expecting 0 flag will be set or reset, it will be 0 or 1. Okay. The same thing you can do it with respect to the particular bit. If jump on bit, if bit is set, bit position equal to 1. Jump on no bit means if the bit position is 0. Okay. So, based on this also you can set, you can perform the jump. After discussing these all data transfer, arithmetic, logical and branching instructions, now we can initialize the loop, right. Suppose I am asking you to multiply the number 35 into 75. Okay. 35 into 75, usually what we are doing is, suppose without using the multiplex instruction, that is you are declaring move a comma 35, move b comma 75, then you are using the mul instruction a b, right. Suppose I am asking you to do the operations without using this instruction, then how you will do it. Okay. So, for that what we are doing means the 35 is 75 times added or the 75 is 30 times added, right. So, by using the simple addition I will do the programming, I will write the programming. So, first I have to declare the value a comma 75. Okay. Then I have to initialize the second data, which is I will do it in R1 comma 35. So, what it means 75 it will be added up to 35 times. Okay. So, before the addition, so what I will planning, I have to add the 75, right, each time 75 only I have to add it, right. So, I will do it in the R naught register, no need of accumulator. Initialize 75 in R naught, 35 in R1, right. Now, clear the accumulator, CLR accumulator you can give it, right. What will happen? Now, the accumulator value is 0. Now, I started to add. So, how I am adding means add accumulator comma R naught. Okay. So, R naught is added means 0 plus 75. So, 0 plus 75 is added and the result is stored in the accumulator, which is 75. Then again I am giving this, then 75 plus 75 is added, right. If I am giving again 75, by the R naught we can add it, right. Then how long I have to add it means based on the R1 register 35 times. So, here one of the special instruction or you can use it DEC R1, right. So, the R1 will be decreased for every addition, then I will do the jump on no 0, because here we have to use the conditional jump. Jump on no 0 means where again do the addition here. Okay. So, here I have to move it. So, till occurring of R1 to 0, for every addition 0 plus 75 is added, then the 35 become 34, again 75 is added, here it become 33. So, this process will be repeatedly doing. When the R1 register value reaches 0, then it will be exit from the loop. Now, the accumulated value is the resultant value. Wherever you want, you can store it, or you can stop the program. To stop the program, we are using the short jump here. Okay. So, this is a way we are initializing the jump instructions for initializing the loop. For inserting the loop, you can use the jump instructions, either branching instructions, that is either conditional jump or unconditional, you can use it. In today's session, we have discussed about the instructions like logical instructions and branching instructions, right, with some arithmetic instructions. How to insert, that is jump instructions for declaring the loop. Along with that, how to perform the logical operations. Logical operations are the bitwise operators, how to perform AND, OR and exclusive OR, right. Then how to perform the signed addition or unsigned additions, and how to perform the multiplication without using the multiplication instructions. That was discussed on today's session. I hope you have understand how to write the simple programs. Okay. So, we will discuss some simple programs in the next episode.